All right, good. Welcome back, everybody. This is AE317, Flight Mechanics and Performance. Today is a Thursday, February 4. Let's just get started, yeah? Okay, so where did I, oh yeah. Did you get my email? No, well, no, before that, like Tuesday, right after the class. I was fairly humiliated, saying, "Wait a second.
Oh, the note correction.
The note doesn't.
Yeah.
Well, the note doesn't make any sense. What's this? And that's the note I created. It doesn't make any sense to me. So I discovered error, page 8. Did you get the email? Did you replace it? Okay. So that's where we start. Okay. So last class we covered iced-tea and iced-tea ground. And then page 8, I got stuck because, wait a minute, what's this kind of thing? So this is the actual page 8. Here is the example problem, A13. So hopefully you got my email replaced this page. There was a huge error. Okay, I didn't even realize. Okay, so we are going to start from here today. Page 8. Okay. All right, so before we begin, let's just take a look at today's update. Not the arrow. Just keep pushing it. I was even waiting in front of the aero classroom today. And it was so, I don't know. So it almost seems like teaching aerodynamics is my job and teaching this class is my hobby kind of thing. This is time to relax, because I don't have to teach, because you guys know that. Aero people, I have to literally whip it and train it up, and otherwise, okay, you know that, do you? Connor, you took my aero class. I'm a different person in aerodynamics. I have to change my personality.
Are you? Right now, my roommate is taking your aerodynamics.
Oh, cool. Class. Yeah. So he has a different expression of myself. It's a human character I just created. It's a virtual reality. That's not me. I'm pretending. It's like an actor, So this class, I don't feel like I'm teaching. I'm just covering some fun stuff, and then you guys do a fun project. Yeah, and then I don't have to repeatedly teaching the basic stuff you already know. Okay, so let's just take a look at it. Which one is a new announcement? Since Tuesday, we got 2 new announcements. One is Wednesday, February 3rd announcement. The take-home quiz 1 has been graded. Almost everybody got 10 out of 10. Of course, that's fine. But if you didn't do that, here is a solution. So solutions posted here. If you click here, solutions page, this is a solution of the quiz 1. I guess if you did the party, that really means probably you used the Bernoulli. Trusted Ernie. You trusted Ernie. Ernie, well, you don't trust the bird. Trust Dr. H, but Ernie is Avatar. Okay, Avatar may say wrong things. Okay. So if you use the Bernoulli, whoops, that's a big mistake. But if you use like a compressible form of Bernoulli's equation, which is called energy equation, or isentropic relations, you can use that to solve this problem. Okay, so take a look at it. This is a solution. Okay, and all right, and also quiz 2. This is quiz 2. This is due.
That looks familiar.
That looks familiar. Well, I don't know. If you know how to do it, you just share it with your teammate, that's fine. If you don't like that, just to stay quiet and do the right thing. Anyways, this is the take-home quiz 2. And this is due Tuesday next week. Okay? Question? Let's take a look. Okay. So this is something called panel method, vortex panel method. Vortex panel method was covered in aerodynamics. There's a note already posted in the home page. So you can take a look at panel method. What's the unit? Unit C3 or something like that of aerodynamics notes. And then one of the main thing of a vortex panel method is each panel you are going to compute pressure coefficient of each panel. And then you end up having pressure coefficient CP distribution over top surface, bottom surface, plotted against the code, which is 0, x over c equal to 0 is leading edge, x over c equal to 1 is the trailing edge. Of course, you know x over c, normalized code, okay? And then, of course, the area bounded by upper and lower surface, which is area like this area represents the lift coefficient, CL, lowercase. Section lift coefficient can be computed by plotting the CP distribution over the top and bottom surface, okay? Then you can determine lift coefficient. That's how your software X-Flyer 5 determines lift coefficient. So in order to get started for using software, you have to understand how the panel method code actually compute the lift coefficient. This is a very basic understanding of how pressure coefficient distribution relates to lift coefficient. Okay, and very simple. You are going to use Excel spreadsheet. You can use MATLAB if you want to, but suppose, okay, if you use MATLAB and did a completely wrong thing, because I have no clue, I don't want to even look at your MATLAB code inside, so you can probably very tiny, puny partial credit. There's a risk for it, yes. Well, you can do it, of course. As long as you do the right thing, I don't care. But if you do wrong thing, and then if you fail to explain, oops. Okay, well, you can do it. But Excel actually making sense, because this is numerical integration to determine the area bounded by those two curves defined, okay? Those curves are plotted based on the data set. This is called numerical integration. What kind of technique is it? Do you remember the technique? What kind of numerical integration technique you are using here? Trapezoidal, yes, trapezoidal integration method. That's right. So it actually makes more sense to use Microsoft Excel because you can actually visualize how to integrate the data set to determine the area. If you use MATLAB, I mean, chances are you can code up trapz function to do it. It's like 2 lines to finish. But you know, if you do a wrong process throughout and then you fail to explain, oh, I used the wrong way of trapz, you probably get, I don't know, 1 out of 10, something like that. So again, bottom line of doing project is you know what you're doing. That's the bottom line. You're not using software without thinking. That's a very common thing for aerodynamics. So I'm aero students right now, I think they're going through like a third quiz and second homework. Bombarded every day doing something. Of course, it's typical for aero. Nothing wrong with that. I intentionally doing it. So, but this class, of course, yeah, if you have seen it, done it in aero, yeah, sure, you know how to do it. But this is very basic idea of panel method. Okay. So let's go back. So right now we are doing Unit A1, and right after that we are going to continue on Unit A2. This is all about foundations of aerodynamics, low speed and high speed at the end of it. No, it's not. High speed is Unit B. So I'm covering those things, and then right after that, here is tons of materials given. This is all about panel method. Okay. So before you start doing phase 1A, the very first phase of your project, you're going to basically run by yourself. This is self-paced tutorials of panel method, because that's what X-Flyer 5 is. It is a panel method code. So to begin with, this quiz will help you to get started. Okay? So this is a very, very, very basic way of computing lift coefficient out of pressure, surface pressure distribution. This is one of those many things that the panel method can do. Okay? So going through this material, if you didn't take aero from me, is going to help you solve this quiz 2. So, okay. If you find someone who took my aero, well, just to team up with those people. It's easy, if so. And then squeeze out as much information as you can get, and then dump it. And switch the team or something. I don't know. I'm just kidding. Don't do that, please. Okay. Well, as a team, you run together. Any question? Anybody? Making sense? So quiz 2, if you didn't take my arrow, it may make you think a little bit, but it's not so bad. Okay, it's not so bad. Any question? Okay, so lots of hint of this quiz actually comes from here. Panel method. Okay, so I would recommend you going over it. Okay. All right, so today let's pick up from page 8. Okay. Example A13. Now, I'm recording. Okay, good. Do you have any question, those two online people? You got any question, Joshua and Matthew? Doing okay?
Doing good.
Okay. All right, thank you. All right. So now let's just take a look at example A13. Now, in last class, we looked at the airspeed calibration process, something called, airspeed calibration process, something called ICE-T and ICE-T-G. So airplane basically spits out the indicated airspeed to begin with. This is data off of your instrument. Now that indicated airspeed, first of all, you need to calibrate it by, fixing data of a pitot-static probe itself. This is something called position error or installation error of a pitot-static tube. And next step is you're going to multiply by the F factor. You're going to come up with the equivalent airspeed. F factor is given here, okay? So this is just a data set, something called F factor. The next step is, since you want true airspeed, you can only get true airspeed only if you know the actual density. So you have to figure out actual flight density. It usually requires additional information, such as outside air temperature, OAT. So if such a thing is given, you're going to multiply the square root of density ratio to determine true airspeed. Now, true airspeed, if you have a crosswind, will be different from ground speed. So you're going to finally correct up with the ground speed, okay? Crosswind. So this is the process, something called ICE-T-G, okay? So let's just take a look at some examples for that. Page 8. Yeah, go ahead. Okay.
Are you planning to take attendance at all?
Ah, good point.
On it.
That's right. Yeah,
I left my
I
avatar in,
probably
in my
think
room.
that attendance is so non-important, so I just keep forgetting. Anyways.
Should we not remind you that?
Yeah, you don't have avatar, but I know you, that's fine.
Okay.
I don't think we need avatars.
But do I have to have one?
I need to take my avatar and
And this is Connor, this is Matthew. Okay, that's it. Because problem is, I never use this attendance anyways, no one asked me. And then they actually force us to take attendance, and then we keep asking, why do we need to? Well, it's required, and then they never use it. Okay. All right, so let's continue. Example 3.3. An aircraft flying at 300 knots. Like I said, knots. This is a nautical miles per hour. Okay. So nautical miles per hour is more or less it's a horrendously non-standard unit, but we oftentimes use that for airspeed of aircraft. So nautical miles per hour. Okay. So 300 knots true airspeed. Okay. Oh, so true airspeed is given. Experiences a 50 knots tailwind. Tailwind. Okay. What is its ground airspeed? This is almost like instant answer. What is it? Let's pick up an equation. Ground airspeed Bg is equal to true airspeed B infinity plus B wind, crosswind. Okay. Okay, so okay, 300 knots Oh, plus or minus?
Plus.
Plus, okay, because it's tailwind, okay? If it's a headwind, you are going to subtract it, okay? So this is 350 knots. That's it, very simple. Next question. An aircraft is flying at the 20,000 feet pressure altitude. Oh, what do you mean by that, pressure altitude? Somebody please tell me. Ooh. 20,000 feet pressure altitude means 20,000 feet exact, right? If you drop down the tape measure, it's exactly 20,000 feet. Does that mean pressure altitude?
No.
No way. It's not. No one knows if it's really 20,000 feet. But what do you know instead? Oh no, pressure you know. Pressure you sense this value. That corresponds to, if today is a standard day, 20,000 feet altitude. So what is that pressure your airplane is sensing right now? I think you have to look at something.
You have to look at standard atmospheric table.
That's right. So let's take a look at standard atmospheric table. It's given somewhere. Oh, it's here. Handout A2. Or right here somewhere. Yeah, standard atmosphere handout A2A. I think this is table. Yeah, here we go. So this is given already. So it's atmospheric table. This is coming straight out from aerodynamics. So 20,000 feet, right? So let's just go all the way down to 20,000 feet. This is 2 meters. Okay, 20,000 feet. Okay? So this is a 20,000 feet. So airplane is probably not flying at the 20,000 feet altitude, okay? But airplane, as it flies, this is the pressure the airplane is sensing. This is the static port of the airplane sensing this much pressure. The value is 9.7327 times 10 to 2. This is the unit of PSF, okay? Pound force per square foot, PSF. So if your airplane is sensing this much pressure as it flies, and then the airplane defaults back to the standard property table, which is already integrated within your instrument, thinking that if today is a standard day, I'm probably flying 20,000 feet, okay? Based off of the information that I have right now, I'm having information pressure. It's called pressure altitude. So which one is a real value? Which one is just the estimate? Go ahead.
Pressure is the real value.
Pressure is a real value. 20,000 feet is just estimate. No one knows if it's 20,000 feet. Okay? It could be a massively non-standard day. It's a heavy rain, snow, very high or low temperature, whatever, whatnot, right by the big mountain, right by the ocean. I don't know. Okay? We never know. 20,000 feet is just estimate. So you're not going to trust in it, but you know the pressure instead. That's called pressure altitude. Let's go back. Okay, so pressure altitude, 20,000 feet really means that you know the pressure. Okay, so which is, this really means you have to interpret, we know the pressure, P is equal to 973.3 pound per foot square. Am I right? Am I right? Is that the correct number? 973.3. Yeah, okay, that's right. 973.3 pound per square foot. That's the pressure. That's the meaning of pressure altitude. Okay. So that means flying at the 20,000 feet pressure altitude means 20,000 is estimate, but we know the pressure. Okay, good. The indicated airspeed of flight is 205 knots. If the outside air temperature OAT is given minus 20 degrees F, the position error is minus 5 knots. and there is a 40 knots headwind, what is the aircraft's ground speed? Well, now this is something real. Okay. So let's begin with indicated airspeed. Okay. So indicated airspeed VI, indicated airspeed 205 knots, right? So starting from here, you are going to have calibrated airspeed. Calibrated airspeed is indicated airspeed and then plus delta P position error. So calibrated airspeed is 205 knots minus 5 knots. So you correct it to 200 knots. Okay. So this is the first step. Second step is equivalent airspeed. Okay. So equivalent airspeed BE is equal to F factor multiplied by BC. What is the F factor? Can you look it up? What is the F factor? 0.987. How did you do that? Okay. So calibrated airspeed is 200. 200. Calibrated airspeed 200, and then pressure altitude 20,000. So this thing. So you pick up this value 0.987 F factor here. Then you're going to multiply with it. Okay. So now 0.987 times BC. BC is 200 knots. What is the equivalent airspeed?
197.4.
197.4 knots. Any confirmation? Any confirmation?
Yep.
Yep. Good. Good. Okay. So this is equivalent airspeed. Usually, equivalent airspeed is the lowest possible airspeed you can get. In other words, suppose if the density is a standard sea level value, this is how much airspeed you can get airplane's force generation capability. Okay. The next step is, what's next step? True airspeed we want. Next step, true airspeed. True airspeed B infinity. Usually you can never get it unless you are given extra information, in this case, OAT, outside air temperature. You need to have that. So in other words, outside air temperature is given, which is minus 20 degrees F. Let's just add the 460, making it Rankine, which is 440 Rankine. Okay. So this is one additional information you need. If this information is not given, that's it. You can't get through airspeed. Okay. Now, what's good for that? If you know temperature, you can actually compute the actual density of your flight altitude. Density is equal to pressure P divided by RT. Pressure is given, of course, you're sensing it. 973.3 pound per feet square. Gas constant 1,716 foot-pound slag Rankine. Temperature is 440 Rankine. What is density? If you're online also, you can basically announce your number too. If the in-class people is too quiet, go ahead. What's the number?
0.0013.
0.0013. I think 128 something.
1289.
89. Okay. 1289. Any confirmation here? 0.00 about 13. 1289. Confirm. Confirm. Okay. Good. Good. Unit is slug cubic foot. Again, I'm going to stick as much as I can standard units, except knots, nautical mass per hour. That's a terrible non-standard unit, but people use it. So, okay. Next step is obviously, in order to get the true airspeed to be infinity, of course, you're going to pick up equivalent airspeed and then multiply square root of density ratios. Density of sea level divided by density of infinity. Sorry, let's just put the infinity here. Density infinity, this is actual density at the flight altitude. This is also P infinity, actual pressure, static pressure at the flight altitude. T infinity, this is outside air temperature. So let's just put all infinity here, free stream. In other words, your own speed. Okay? All right. So equivalent airspeed is, we know, 197.4 knots multiplied by square root of density ratio. Do you guys know standard sea level density somehow?
1.6.
Oh, no.
So,
0.002377, something like that. So we oftentimes use the standard sea level density, so I kind of almost remember. So this is standard sea level density, so that's per cubic foot. And actual density of the flight altitude, we computed 0.001289 slugs cubic foot. Okay. So if you compute this, square root of density ratio multiplied by 197.4 knots, what's the value here?
268.06.
68.06 knots. Any confirmation? So this is the true airspeed. However, you have a headwind. Ground speed is different from true airspeed. This is B infinity plus velocity of crosswind. So in this case, 268.06 knots. Then you subtract headwind 40 knots, which is 228, about 228 knots. Okay, so this is the ground airspeed. Okay, so let me just point out a few important things here. So this is G, ground airspeed. This is true airspeed. And this is equivalent airspeed. And this is indicated. Airspeed. This is calibrated. Airspeed. So you have to go through step-by-step process, starting with indicated I, go to calibrated C, lowercase c, equivalent. Lowercase means this is the lowest value. And then through airspeed T, and then ground airspeed. So ISTG, step-by-step calibration process. So you have to do this all the time, okay? from the instrumentation indication to true airspeed to ground airspeed. Okay. Any questions? So today, let's just take a look at the wind tunnel. Wind tunnel is, of course, you guys probably took. Did you take wind tunnel class? Okay, some of you actually took it. So if you didn't take it, well, are you gonna take it? Are you gonna take it near future, or you have no plan to take that class?
I need to, I don't know.
Are you air track?
I'm sorry?
You're air track, right?
Yes.
That means you have to.
Yeah, you have to. Yeah.
That means you can't choose. Okay, anyway. So you're gonna take wind tunnel class anyway. So wind tunnel is actually a very simple device. It's controlled by usually Bernoulli, if it's raw speed. So let's take a look at the mechanism of raw speed wind tunnel. Everything's Bernoulli, as long as Mach number is less than 0.3. Okay, so this is raw speed wind tunnel. Okay, the velocity of the air in a wind tunnel's test section is measured either by a pitot-static tube placed in a test section. Have you ever seen that? I think I showed you a picture in aerodynamics, but I can sort of show it too. Okay. I think you've seen this over and over in aero class, but pitot-static tube in the wind tunnel testing is this. Okay? So you're going to insert pitot-static tube in the wind tunnel testing, and of course, center tube and side port is coming up, and then those two things are connected to something, connected to like a black box. And then you read off, and oh, you know, what's the speed? 5 inches of water. And then I have no clue what I'm saying. And then Dr. Ash was Dr. Ash was retired. Sorry. Who's doing it? Wind tunnel.
Traub.
Dr. Traub. He's nice. He doesn't explode. Dr. Ashwas always carry a pistol. Oh, he's a retired Air Force person, of course. And then he's the guy who created this class. And then he retired, dumped everything to me. That's a fact, okay? So this is the black box. You're going to connect up with this black box and measure the airspeed, right? So of course you know how to do it. Suppose if somebody says 5 inches of water, what's the airspeed in miles per hour? Oh, you know the ballpark figure. 5 inches of water. How much miles per hour? I mean, didn't you take it? I mean, wind tunnel class? You can tell. About 100, okay? 100 miles per hour is 5 inches. If it's standard day, sort of.
This was a quiz.
This was a quiz in Aero. Yes. Thank you very much for supporting Aero.
Yeah, it was a quiz.
Like 99 something out there.
That's right. Okay. I think your roommate is going through that painful process. Anyway, so this is what I'm talking about, okay? So that's one way, but pitot-static tube placed in the test section, or number two, you're looking at it here, two static ports. One is on the test section, the other one is a settling chamber, okay? So if you do that, you're going to measure the pressure difference for those two static ports and then apply Bernoulli's equation combined with continuity. Have you seen this equation in fluid mechanics? Yes, I've seen it. So this is essentially fluid mechanics. Combined two equations. One is continuity, one is Bernoulli. Okay? And then you can determine airspeed. Here we go. So this is a wind tunnel test section airspeed equation. Very simple. Okay? Let's take a look at the next page. Okay? So this is the low speed wind tunnel. That is similar to the one shown in the figure here. Settling chamber with cross-sectional area 10 meters square, and then test section with a cross-section area 1 meter square, which is a very sharp contraction. 10-to-1 ratio, which is pretty sharp. I don't know if it's normal. When the wind tunnel is run in standard sea level atmospheric condition, again, this means pressure, temperature, density, all standard, or what is it? Let's be careful about that. Okay, so pressure, air density, standard sea level. Okay. That's right. A manometer connected between static ports in the walls of the settling chamber and the test section has a difference in the heights of its fluid columns of 50 centimeter. What are the maximum test section velocity magnitude and the mass flow rate through the test section of this wind tunnel? Let's find out. So what is the equation? You have to pick it up to begin with. In other words, this is airspeed determined by using manometer, U2. Okay, this is probably taking you all the way back to fluid mechanics. Now, I have a huge complaint nowadays because the fluid mechanics professors don't even cover wind tunnel these days. And then I'm mad. I'm really, really mad. So my frustration goes right into the beginning of aerodynamics class. So I give quiz, which is essentially this kind of quiz. Okay, figure out wind tunnel test section airspeed by looking at the manometer, blah, 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 and then students usually screw up. I know that because professors of ME, they don't cover wind tunnel at all in fluid mechanics class. Okay, so, but I cannot blame those people. I can only beat up students. So that's why I give quiz at the very beginning. But the students just pick up those things very quickly. Right? Didn't you see this problem?
Yeah.
I mean, if you took my arrow, well, okay, good. You remember that? I hope so. If you don't remember, I can resurrect that quiz and make it due right tomorrow.
No.
Nope.
Nope. Okay.
Did it once, don't want to do it again.
Nope.
I haven't followed.
So you are going to actually start with manometer equation because it's a manometer. Manometer equation. So manometer equation basically says that, okay, so this end is a cross section 1, station 1. So pressure, whatever the pressure here, P1, let me just zoom in a little bit more. Okay. So pressure P1 at this settling chamber go all the way to here. So this is the pressure P1, right? Okay, pressure P1 here. The other side is right here, pressure P2. Which pressure is high pressure? P1, of course. Otherwise, how can you suck the air in anyways, right? P2 is lower pressure. P1 is higher pressure. That's why air is sucked in. Okay, good. So let's just to think straight, okay? Sometimes engineers think too much.
That is true.
Yeah. So P1 minus P2. So P1 minus P2, obviously P1 is higher pressure, P2 is lower pressure, which is equal to, how can I determine such a thing? Manometer equation. What's that? Rho GH, of course. Rho G, this H, delta H. Okay, so we are just going to plug in, so P1 minus P2 is equal to, what's rho of water? This is water, right? Does it say so?
Actually,
It doesn't say anything?
It doesn't say.
it really is.
It doesn't say anything?
No.
Wait, it says similar to the one in the previous figure.
Previous figure.
Oh, that's
Okay,
useful.
so
But that one doesn't say water.
That doesn't say anything.
That's very
It's
useful.
water.
It's water.
It's doing water, I like water.
Is it water? Okay, so I found a massive problem here. Again, so this is the fault of a textbook also, who is essentially Air Force Academy. This is water, okay? Let me just add water. Okay. Yeah, of course, water. It's like a common sense, inches of water. That's what you use, right? Okay, water. How's that? So that's probably included within. Because whenever you talk about how fast that wind tunnel can go, you always use inches of water, right?
Yeah.
So this is 50 centimeters of water. How's that?
Sure.
And then people keep asking, what's the meter per second then? Or kilometer per hour or miles per hour? I want to know. That's the speed. Okay? 50 centimeters of water doesn't make any sense. Okay, anyways. So let's move on. So assuming this is water, What's the water density?
1,000.
1,000. That's right. 1,000 kilogram cubic meters. It's water density. Gravity is, of course, 9.8 meter per second square. Delta H given is 50 centimeter, which is 0.5 meters. So if you compute through it, well, I can do it without calculator. 4,900. Easy. What's the unit? Pascals, Newton per meter squared. Okay, that's right. Good. So next step is, of course, P1 minus P2. What's the P1 minus P2 anyways? What do you call that stuff? In this case, no, in this case, not. If it's pirostatic probe, pressure difference between center tube and side port, it's called the dynamic pressure. This case, it's not. So we are going to plug into the equation in the previous page. B2 is equal to square root of 2 times pressure difference, P1 minus P2, density rho times 1 minus area ratio, A2 over A1 square, close bracket. Now, interesting question is, this is source of many mistakes. I can guarantee if I do this quiz in fluid, probably more than 2/3 of the class do this mistake. What's this density? Is this water density?
No.
What's this density?
Air.
Density of air. Be careful. Okay. Well, I can guarantee, if this is a quiz or exam of fluid mechanics, probably half of the class plug in density of water. Then I viciously grade it. Okay, anyways. So this is 2 times P1 minus P2, 4,900 Newton per meter square. Density is, density of air, let's assume standard C, but what's the density of air standard C over SI unit? Do you guys know that? I know that. It's 1.225 kilogram per cubic meters. I actually use this quite often in this class. I kind of memorize it. 1.225. Okay. And then 1 minus area ratio. Area ratio is 1 to 10. So 1 meter over 10 meter. So 1 over 10, this must be squared out. Be careful. And this is going to get SP. This sounds awfully like fluid mechanics. What's the value?
$89.94.
89.94. Any confirmation?
Yeah.
Okay, good. So this is the internal test section SP. Based on the 2 pressure taps on the wall. In other words, you're going to measure the static pressure at the test section and also settling chamber. Pressure difference is going to determine the airspeed at the test section. Okay, and then also, if you want to, you can determine the mass flow rate. Okay. So mass flow rate in this case is m over dot is either rho 1, A1, B1, or rho 2, A2, B2. You can do either way. So in other words, you can determine mass flow rate either using the property at the settling chamber or test section. Why you can do such a thing? What kind of, is this a Selby or something? This is called continuity, that's right. This is a continuity equation. That's right, that's what you're thinking. Now, in this case, you can even further simplify though. Because we don't need to talk about mass flow rate. This is incompressible flow. I mean, this is low speed. Okay, so again, oftentimes you're going to probably don't even look at the density. Density doesn't change, right? If it's low speed. But anyway, let's just plug in. density is 1.225 standard sea level density of air. Cross-section area, which one? Let's just use 2, okay? Cross-section area 2, test section is 1 meter squared. Velocity, oh, that's fine, because we got V2. 89.94 meter per second, so this is test section airspeed. So this is going to give you the mass flow rate. About 100 something.
Yeah, 110.17.
110.117. What's the unit?
Kilograms per second.
Kilogram per second. That's right. This is the mass flow rate of this vector. All right, so it's a fairly simple deal. Okay. So today, actually, the rest of the class, I have a series of video I wanted to show you. Wind tunnel testing is quite important. So I brought a few videos for you. Okay. Let's just take a look. Okay. Actually, those videos you can actually take a look at by yourself if you want to. Save. Okay, let me just go to course homepage once again. If you go to course homepage and click on the video page, okay, this page actually shows you all the captured lecture videos. At the same time, oftentimes I also put instructions media videos, okay? You can click and take a look at any time. So I'm going to show you today smoke wind tunnel. Did I show it to you? No. Okay, let's take a look. This is basically so small. That's good. Okay, good. All right, so this is the smoke wind tunnel test demo. Suppose you are online. Can you see this video? Okay. Matthew and Joshua?
Yes.
Yep.
Okay, is it smooth?
Yeah.
Okay, that's good. So this is a smoke wind tunnel. Okay, flow is from right to left. Of course, at the upstream of this test section, you have a smoke wire. And then creating smoke droplets becomes tiny particles, smoke, and then carried across the test section at airflow. You can pitch up and pitch down the model. And then you can do flow beads. This is flow visualization technique called smoke wind tunnel. Now, this is surprisingly not much information you can get. Everything is qualitative. Okay, flow around here is smooth. Flow around here is not smooth. Or this is steady. This is unsteady kind of thing. It's just a very qualitative thing. But okay, so this actually tells you an important thing. Aerodynamics is so tough. One of the reasons here is it is not easy to quantify it using equations. It's very limited. In order to quantify something, you have to apply mass. In order to apply mass, flow field must be steady, first of all. And if the flow field is steady, you can see some lines here. So those are the lines you can visualize. This is originally a streak line, but if the flow is steady around here, this is sometimes called streamline. If you can define streamline, you can apply Bernoulli's equation, Euler's equation, energy equation along that line. Okay. However, if the flow is unsteady around here, can you apply any equation here? Yes, you can possibly, but the equation is now, okay, how many particles can you see? I don't know, 1 million. Maybe 1 million partial differential equation second order, non-linear, to represent flow field. That's called computational fluid dynamics. You can never do it by hand. And you can never do it by your tiny puny laptop. You need a supercomputer monster. Still, you can only do certain things. That's what you call CFD. The nature is, of course, you can never do such a thing by hand, right? So that's why people have an image of, oh, aerodynamics is so difficult. No, aerodynamics is not difficult. Flow field is so complicated. Aerodynamics is easy because we can only do certain things by hand. And we only cover only things that we can do by hand. So aerodynamics is actually so easy, so complicated, but the flow field equation is so like a scary complicated, and they have an allergic reaction. Oh my goodness, I can never understand this kind of equation. It's a second order partial differential equation, nonlinear type. And then it's a vector equation, so you have 6 components, something like that. Have you ever seen that? Maybe a Stokes equation. All right. And I have a low speed wind tunnel testing I did in the past, a few years ago. Actually, not a few, long time ago, almost, I would say. So I'm going to show you some videos of a wind tunnel testing. Okay. So first of all, there is a system, something called the mid-air refuel system. Sorry about that. I just keep opening arrow page. I don't know why. This is not the arrow. Sorry. Okay. Yeah, let's repeat. Yeah, this is actually happens quite a bit. You know, this is helicopter. Helicopter pilot. If pilot is trying to be refueled with this device, this is called paradrogue. Mid-air refueling. Pilot's tendency is, you know, if this device is unstable, in other words, goes up and down and up and down, trying to follow through those things. That's a basic nature of pilot. If this paradrogue is unstable, going like this, I mean, it's just trying to follow through that motion. This can happen anytime. Okay, so one of the research subjects was we wanted to have a much more stable flight device. And also at the same time, this is a helicopter and also jet airplane. Those are 2 different speed range. So the single device cannot cover both. We wanted to have a single device actually go for low speed and high speed both. It's called variable speed paradrogue. I think they made it happen. Now it's patented by Boeing. So Boeing took everything. Anyways, so
do you know what aircraft is refueling?
That's right. Yeah. No. This is KC-135 is like a boom type. Boom type is a. It's not this one. This is a fried paradrogue. Yeah. So this is more like a smaller type and a much more like a flexible type. Now there's no operator needed. Okay. The other one is a boom type. So there's an operator controlling this boom, which is much more stable. This one is a free flight parachute. Okay. So we did some testing. So first of all, good one. So testing. Just a minute. Let me just turn on the audio. Okay, for online people. Okay. So this is a good. If you notice, this is not the regular type of paradrogue. This is a new design. You have 2 different type of parachute cross sections. So if it's low speed, both deflated. If it's high speed, one of them collapses. So if you fly high speed, you can't have much drag. Drag needs to be lowered. But if you're flying low speed, make the parachute surface bigger so that make it higher drag to open. In other words, in order to open this device, you need a drag. This is a parachute aerodynamics. So this is a new design, and then this is okay flight. However, not so okay. This is like fairly unstable.
We're up to 2 more runs after this. We're rolling. Yeah. That's fine. We're getting our parts made, so we're just going back and forth trying to isolate the effects. We spent a 6-pack of beer and 4 hours last night discussing what we were going to do with it all of a sudden.
Okay. So then this is not good paradrop. Now I just realized my voice was in the background noise. I was talking something. Anyways, so this is the paradrop testing. We spent about 3, 4, 5 years doing this test. The wind tunnel you saw was in San Diego, Allied Signal wind tunnel. Cross section was 8 feet by 10 feet. 8 feet by 10 feet. You can fit the car in it. It's so huge. And then, you know, the fan, wind tunnel fan is like as tall as that AC1. A huge fan. It's unbelievable. Huge fan is spinning like a 4-blade, wooden blade fan, as tall as like AC1 building. It's huge. Huge wind tunnel. It costs a lot of money though. Energy cost is $5,000 a day if you run it. Yeah. And then operator fee is like $5,000 per person. They got like 5 operators. And then other fees. It costs fortune to run this kind of wind tunnel. Okay.
Not only $5,000.
All right. Okay. So any question here? So this is the wind tunnel testing. All right. So let's move on today. Okay. Next page is, of course, I'm going to now move on to airfoil, which is a cross section of a wing to begin with. Airfoil is somewhere you are going to begin your design. You're going to choose your cross section when you design airplane. In other words, your choice of cross section is going to have a fundamental impact on your character of your airplane. If you want to have a low speed, high capacity, payload type of airplane, such as, I don't know, firefighter, you're not going to choose certain cross section, of course. You're not going to choose an airplane like sitting next to the bookstore, right? That airplane is a horrible airplane for low speed. Of course, you're not going to choose that. And then, of course, high-speed airplane is completely opposite. But some of the airplane in the transonic region, they actually have a fairly thick cross-section, supercritical shape. So there are lots of information when you choose cross-section of airfoil. Now, if you choose to go for heavy lifting airplane, you have a tendency to have a thick airplane, right? Very thick. What's your cross-section right now? SAE.
We're not using a NACA airfoil.
You're not using NACA airfoil. You're choosing something else.
It's C1223.
Oh, okay. Got it. So there must be some reason. In other words, your choice may have a significant impact on your airplane performance at the very end. And then if you do poor job at the stage of your choice of 2D cross-section, problem is, no matter how good your wing is, oops, it doesn't fly that well. Okay, it's a fundamental problem. So you're going to have airfoil and then airfoil cross-section, okay? Now, airfoil is a device to create lift, but at the same time comes with a drag. So we are going to kind of discuss a little bit about what is the mechanism of an airfoil creating a lift. Now, as the flow moves over the surface, obviously because of its shape plus angle of attack, Now, angle of attack, we're going to define that later, but flow on top surface is going to, of course, accelerate at certain regions. Accelerate at certain regions, okay? Flow comes in, accelerate, flow comes in and accelerate, look at this. This is a plot of velocity over the top surface, plot of the velocity of top surface. So right here, flow is accelerated and then hit the peak point. So this is the fastest velocity right here, fastest velocity right here. And after that, it just decelerate, and then something here, accelerate again a little bit, and then go back to zero. So this is the velocity distribution on top surface. And bottom side is, well, starting from here, sort of mildly accelerate, but it doesn't do so much, and then depart from the surface. Because of the velocity distribution over the surface, have you ever heard of a velocity pressure coupling? Velocity pressure coupling. What's that? Velocity pressure coupling. Have you ever heard of this term? In other words, if you know velocity, you know the pressure. If you know pressure, you know the velocity. What is that? Bernoulli's equation. Velocity pressure coupling. Okay? So once you know the velocity distribution over the surface, top surface and bottom surface, you can tell pressure distribution on top surface and bottom surface. As a matter of fact, it's the exact same shape. Okay. So having said that, once you determine the velocity distribution over the surface, you can determine pressure distribution over the surface. I guess you guys did it in Aerodynamics 1, the project called flow over circular cylinder. Didn't you do that? Yes, you did. Okay. Yes, you did. That's a velocity pressure coupling. Okay. So now you are going to determine the area between upper and lower surface. This area. What's this area? Lift coefficient. Lift or lift coefficient. If you use the pressure, it's a lift force. If you use the pressure coefficient, it's a lift coefficient. Okay? So surface, you have two different types of distribution. One is a normal force, which is the pressure. One is a shear force, which is skin friction. If you include the viscosity, you're going to have a skin friction drag coefficient distributing over the surface. But it usually doesn't come into play for the creation of a lift itself. It's just to contribute to the drag, skin friction drag coefficient. So lift is usually coming from normal force, which is the pressure. Okay? So this is a very basic thing of an airfoil. So now you're going to determine the chord line of a cross section. Chord line is straight line connecting between leading edge to trailing edge. This is called chord line. Okay? And if you integrate all the pressure and the shear stress distribution over the surface, you're going to come up with a resultant force. Okay? Resultant force can be dissolved into two components. One component of the force, which is perpendicular to the incoming direction of the flow. This V infinity is called free stream. So one which is perpendicular to the free stream is called the lift. One which is in the same direction of the free stream is called the drag. Okay? Now, the angle between incoming free stream to the chord line, this alpha, you guys know this is angle of attack, AOA. Okay? So very basic things of aerodynamics. Now, you can determine how much lift you can produce over the surface. That means you're going to resolve all the pressure which is acting on each small tiny segment of the surface of an airfoil, okay, which is going to make an effect on small tiny segment of your code. this actually end up having this much component of the force developed due to the pressure distribution over the surface. If you integrate this component of the force all the way from leading edge to trailing edge, what do you have? Lift. Okay, that's it. Didn't you do a quiz? Do you remember quiz 6? Yeah. Do you want to do it again? No. This is basically you're going to mathematical integration of the pressure distribution over the surface from leading edge to trailing edge to determine lift coefficient. Didn't you do that? It's one of those obnoxious quiz you hated to death. Very mathematical.
Oh, that one.
Oh, that one, yes. I think I can show that because I'm thinking of doing the same quiz this semester too. Let me show you that. Actually, what kind of quiz am I talking about? And then if your reaction is, I mean,
No, it wasn't hard. It was
eh? Wait a sec.
Let's not.
This one.
Yeah, let's not.
And then if your reaction is, oh yeah, we did it, we know what to do, I'm not going to do it. But if your reaction is, what's this? Well, let's do a quiz. Do you want to do this quiz? This is like, everybody hates this quiz.
We only hate it because it took a while.
Yeah, it's a lot,
Oh,
right?
yeah, it probably takes, I don't know, it was like 15 minutes to me.
Hard. It's a lot, right?
It took you like 2 days.
No.
Oh.
Like 45 minutes maybe.
So do you want to do it?
No.
Like a special quiz?
No.
So this is what I'm talking about, okay? So this is basically surface pressure and the shear stress distribution. That's what I'm talking about, right? Look at that. So this is surface pressure and shear stress distribution, upper and lower surface both. If you integrate from leading edge to trailing edge and then resolve into perpendicular parallel direction, you get the rift. Oops, 5 more minutes. So that's what I'm talking about here. I don't think you want to do this quiz anyways, because I did anyways in N 1. Good for you. This is not the N 1. I don't want to grade tons of quizzes, which is screwed up, which is very painful. Very painful to give a partial credit, because I have to read between the lines. I don't know what this person is talking about, but well, I'll give you a 6 kind of grading. Okay, so we are going to stop our discussion here today, and the next class next week, we are going to take a look at the boundary layer, okay? Viscosity involved, skin friction drag due to boundary layer transition, separation, other things, laminar to turbulent. Of course, you know, X layer 5, the software can actually handle those boundary layer models, okay? So let's stop here today. Do you have any questions? Have a wonderful weekend. See you guys back on next Tuesday.
Yeah, we just worked homework on it. You had one day. Yeah, you're supposed to read that thing. Whatever.
Yeah, like materials, it's not like